So welcome back for the second part of our problem. So we already established the stabilizers for our C1. So basically where all the four little squares in our 2x2 chessboard are all colored white. So that would be this one here. So this one. And it is in its own orbit. So it's an orbit with one element only, and we realized that every group member basically fixes this element here in our group. Now let's have a look at coloring C2. Recall that C2 was the little square where I believe only the upper left part, yes, that's correct, only the upper left part is colored black. Now the question would be, which symmetries will leave it as it is? Obviously the identity will do the trick, that's why I put the E here. What else? A rotation, any of the rotations will change the look of this figure, so that won't work. However, a diagonal rotation will leave the coloring as it is. So consider a coloring along these diagonal. Obviously our C2 will remain as it is. So applying in that case R to C2 will give you C2. So long behold, that would be the stabilizers for C sub 2 is equal to E and R. In a similar way, you can figure out the other stabilizers for the remaining orbit members. But what is striking is every one of them has equal number of terms, so which is all 2 in this case. Now let's have a look at another one, C6 for instance. C6, C7, C8, C9 are essentially the same coloring, where we have two boxes colored. I believe C6 was the top 2 colored here. Let's focus on C6. So what group action will keep this coloring intact? Obviously E will be one of them. Another one would be a reflection along the mid-vertical line. So it would leave that coloring intact as well. So that explains the E and the Q. In a similar way, we can find the group symmetries that will leave these coloring C7, C8, and C9 fixed as well. And again, the same, we just observe the same thing here. Each one has 2 group actions, group members, which leave these elements, individual elements, fixed. And you can similarly figure out the other colorings and what group actions will fix them. Interestingly, C16, where all 4 little squares are colored black here inside, either rotation or reflection will leave it intact as C16. So it doesn't matter. Any one of these group actions will just leave it as it is. So long story short, we can now make our critical observation, and the theorem would follow, obviously. So let me actually directly state the theorem itself. The theorem, it's called the orbit stabilizer theorem. So if you have a group G, we can say let G be a group that acts on a set acting on set X, and then in that case we have the following result. For every X in X, we have that the number of elements in the orbit where that member in that particular coloring lives times the number of group members which stabilize, which fixes that element here, that coloring, that should be equal to G, which is the number of elements in our group. In any of these cases, that the 6 coloring patterns that we have, all they all work. For instance, the orbit where C7 lives has 1, 2, 3, 4 elements in it, so therefore OC7 is equal to 4, whereas the stabilizer of C7 has 2 group members, which fixes C7. Long and behold, you multiply these two, 4 times 2 is equal to 8, and no surprise, this is equal to the total number of group actions or symmetries that we have. So that's a very obvious result. Using this result, it's possible to prove one of the first methods for counting the colorings. Let me actually create a little bit more space here and a different color. So that would be our second theorem. The number of distinct orbits, or you can say essentially different orbits, in our example colorings and coloring patterns, is given by the formula 1 over the absolute value of G times the summation over all different members of any given coloring, adding all the stabilizers of every single coloring. And that would be it. So applying this theorem to our problem at hand, the solution to the 2x2 chessboard problem would be basically quite straightforward. Well, to make life easier, I will just come up with a table here. Here are every single element in our coloring, different colorings. And then this is the number of stabilizers that stabilize that particular coloring. So because of we have that table on top that I just presented to you, so consider different colorings: C1, C2, C3, C9, and because I know some of them are really the same, so I will just rewrite them. So C10, C11, for C12 all the way to C15, these are inside the same orbit regardless, so they will give the same result. And C16. For C1 we realized it has 8 stabilizers. For C2 we had only 2 stabilizers, right? So everyone can see here that it's only 2 here, and so on. So every single one of these would be 2, 2, 2, 2. For C6, C7, they're all, so they're also 2s here, all the way to C10. C10 and C11 has 4 actually. C12 through C15, they are all 2s here, so 2, 2, 2, 2. And finally C16 is 8 again. So now we can plug these values into our formula to figure out the number of essentially different colorings. Number of colorings is equal to 1 over, because we have both rotation and reflection symmetries, 1 over 8. And so we basically add up these numbers: 8 plus a bunch of 2s plus 2 plus 2 plus 2. I think I have 4 more 2s, plus 2 plus 2 plus 2 plus 2, and then we have plus 4 plus 4 plus 4 more 2s, 2 plus 2 plus 2 plus 2, and luckily finally we have an 8 here. So you add up all these numbers, I believe you get 48. So therefore 48 divided by 8, so 48 all divided by 8, you get 6. So which is kind of well, what we wanted to show, because we already knew since the beginning of our problem that we have 6 essentially different ways to color. And so this is the first one, second one, third one, fourth, fifth, and sixth. And our problem verifies this result. So it is quite nice to have the desired outcome. Now in the last lecture that I will give, in the next one, we will just realize that this is not a very efficient way to calculate, and rather we will come up with the Burnside lemma. I will even show you a short proof of that lemma. So it's a much more effective way of counting it, because even in the 2x2 case you have 16 different summonds here. It is not very efficient to do it in this way. So we will find an alternative form for this counting orbits formula. So that's it for now.